Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Wisconsin-Madison, and he'll be talking about orthogonal polynomials and some applications.
Well, it's a pleasure to be here. I spent a couple of summers at Bell Labs back when I was a graduate student, and Microsoft Research is probably the best successor we have for what Bell Labs was like at that time. And I'm also pleased to meet Henry. We've corresponded occasionally since he was a graduate student, and this is the first time we've had a chance to meet. I want to tell you about a paper that I should have written 35 years ago. And I regret now that I didn't, because it relates to a paper that Mark Kac wrote back somewhat over 50 years ago. This is a paper that appeared in the Monthly. It won the Chauvenet Prize, one of two Chauvenet Prizes that Kac won. The one, Hearing the Shape of a Drum, is the one most people know, but his first one was on Brownian motion and random walks. And many years after he won the Chauvenet Prize, the MAA put together a volume of Chauvenet Prize winners, and those that were still alive, unfortunately Kac is no longer alive, wrote comments on their papers, and he was still alive then. And he mentioned that a determinant that he had evaluated in that paper had been pointed out in another paper to have been stated by Sylvester. And he said there's no indication that Sylvester had a proof of this. We have no idea why he was concerned with it. But there it is. The determinant tridiagonal matrix with lambdas down the main diagonal, 1, 2, 3, up to n above the diagonal, and n minus 1 down to 1 below the main diagonal. And when you compute the determinant, it splits depending on the parity of n. It's either lambda times lambda squared minus 2 squared times lambda squared minus 4 squared, or lambda squared minus 1 squared, lambda squared minus 3 squared, and so on. Now, Kac implied that Sylvester probably didn't have a proof, and I have no idea whether Sylvester had a proof. But here's the start of a proof that Sylvester clearly could have done. Same argument works for the n by n determinant. We'll just take the 4 by 4, alternately subtract and add the lower rows. So x minus 3, 1 minus x plus 2 is 3 minus x. X minus 2 minus 1 is x minus 3, and so on. And do that for each row with the ones below it. And then add the columns to the left of each column, and you end up with an x minus 1 and x minus 3 in the upper left-hand corner, zeros across that, and the 3 by 3 determinant that's left with x replaced by x plus 1. So d4 of x is x minus 3 times d3 of x plus 1, and then you work your way down by induction. Clearly, Sylvester could have done an argument like that. What isn't at all clear from that is what's really happening. And are there other determinants that one can actually evaluate? And the answer is yes, there are. And this is best seen by looking at orthogonal polynomials. Now, there are two classes of orthogonal polynomials that we know something about. Polynomials that are orthogonal on the real line, and polynomials that are orthogonal on the circle. On the real line, a typical example that you keep in mind are the Chebyshev polynomials. Tn of cosine theta is cosine n theta. Hermite polynomials, Legendre polynomials, and many others are examples. On the unit circle, z to the n is an example of a set of orthogonal polynomials. I'm not going to say anything about the unit circle ones. I'm just going to talk about polynomials that are orthogonal on the real line with respect to a positive measure. Now, x times Pn is a polynomial of degree n plus 1, so you can write it as a sum. Let's see, we got a marker. As a sum, akn pkx is x pnx, where k goes from 0 to n plus 1. Then akn is going to be the integral of xpn pk d alpha divided by the integral of pk squared d alpha, and that's 0 if k is less than n minus 1, because Pn is orthogonal to all polynomials of lower degree. So we only have three terms. Xpn is an Pn plus 1 plus bn Pn plus Cn Pn minus 1. And you can compute an and Cn, and we normalize so that the integral of Pn squared, we call it Hn, and that's going to be positive since the measure is positive. Ordinarily, when one's doing general orthogonal polynomials or using them in numerical analysis, you want polynomials of all degrees to exist. We're going to be specifically interested in cases where only a finite number of polynomials exist that are orthogonal. And the orthogonality, instead of being an integral with respect to a positive measure, is just going to be a finite sum with respect to positive masses. So we get an times hn plus 1 is this integral, cn times hn minus 1 is this integral, and if you shift n down by 1 from there, you get that cn and an minus 1 have to have this same sign. Let me put my glasses on. I think I've got a, yeah. Now, there's a converse to this. If you have a set of polynomials that satisfies a three-term recurrence relation like this, with an minus 1 times cn being positive, then there is a positive measure for which these polynomials are orthogonal. The theorem is known as Favard's theorem. It was proven by Favard in the middle of the 1930s in the Compte Rendu, as a culmination of a series of papers by a number of people that started off with polynomials satisfying a recurrence relation like this with the appropriate positivity. It was known from the orthogonality that all the zeros of these polynomials are real, and the zeros of Pn and Pn plus 1 separate each other. And then people started to discover that if you had a three-term recurrence relation like this, with appropriate positivity, all the zeros of the polynomials would be real, and then that the zeros of Pn and Pn plus 1 separate each other. And Favard finally killed the whole series of papers by showing that the polynomials were orthogonal with respect to a positive measure. However, Favard was not the first person to do this. It's in Marshall Stone's book on linear operators in Hilbert space, but it's in the last 100 pages of about a 700-page book. And most people stop before you get to the last 100 pages because the last 100 pages deal with difference equations rather than differential equations. I read a paper of Freeman Dyson once, and he mentions this theorem and gives a reference to a book by Vintner, Infinite Matrices and Spectral Theory, in 1929, and says Mark Kac told him about this reference. So I asked Kac if that's where he found it, and he said, yes, where else is it? That was the only place he knew it from. Well, where else it is Perron's book on continued fractions from 1912. It can't be earlier than Stieltjes because you need a Stieltjes measure. And Stieltjes has it when the polynomials are orthogonal on a half line. But in fact, it is older than Stieltjes. It goes back to Chebyshev, back to the 1850s, where he had this just for a finite number of polynomials and showed that they're orthogonal with respect to a finite sum. And then to get the general case, you need weak star compactness or some sort of generalized nonsense. Generalized abstract nonsense is what we called it when I was a graduate student. I don't know what it's called now. Now, we can renormalize these polynomials, just setting Pn to be Kn times Rn, and then choosing Kn so that the polynomials are monic. And the recurrence relation is xrn is Rn plus 1 plus Bn Rn plus An minus 1 Cn times Rn minus 1. And so we need that this coefficient is going to be positive. Now we can take that recurrence relation and write the polynomials in a matrix form. Rn plus 1 is going to be this tridiagonal matrix, and it satisfies a recurrence relation because it's, well, let me put back on what we had. It's x minus Bn times this subdeterminant, which is Rn, and then minus An minus 1 times Cn times what you have above that, which is Rn minus 1. So the three-term recurrence relation and writing the determinant representation for these polynomials are the same thing. Sylvester's determinant comes by taking the b's to be 0, ak to be k plus 1, ck to be capital N plus 1 minus k. And what Sylvester had done is to claim that r sub capital N plus 1 could be evaluated. Now, let me put on a chart of the classical polynomials. Hermite polynomials are orthogonal with respect to the normal distribution. Laguerre with respect to the gamma distribution next to the alpha e to the minus x. Charlier polynomials with respect to the Poisson distribution, a to the x over x factorial, summed from 0 to infinity. Jacobi polynomials are orthogonal with respect to the beta distribution. We usually put it on minus 1, 1, so that when alpha equals beta, the polynomials being symmetric, and either even or odd, depending upon the degree, would be symmetric around 0 rather than around a half. Krawtchouk polynomials are orthogonal with respect to the binomial distribution. And it's the symmetric Krawtchouk polynomials with p equals a half that are the polynomials that come up in the Sylvester determinant. Now, the Krawtchouk polynomials in general can be written as what we'll call a hypergeometric function. I'll tell you what that is in a minute, but a sub k is what I call a shifted factorial. It's often called a Pockhammer symbol, but Pockhammer did not, in fact, use this notation. It's just like a factorial. You start off 1, 2, 3 up to n, only now we're going to start with a plus 1 up to a plus n minus 1 with n factors. The minus n here terminates the series because if j is n plus 1, then you're going to get a 0 as a factor. There's a problem with this capital N in the denominator because the series should go from 0 to infinity. And once you get beyond capital N, you get a 0 in the denominator that's going to, in effect, kill the 0 in the numerator with that little n. And you can continue to terminate this series by letting x be 0, 1 up to capital N. These Krawtchouk polynomials are orthogonal with respect to the general binomial distribution on 0n. And to prove Sylvester's determinant and then to generalize it, what we need to show is that k sub capital N plus 1 vanishes when x is 0, 1 up to capital N. Now, I'd like to show how that can be done.
Because the determinant has 0 to that number.
Right. Sylvester's determinant is not the determinant that you get from Krawtchouk polynomials, but it's equivalent to the symmetric one when you shift. You see, they're orthogonal with respect to 0, 1 up to n. And Sylvester's was symmetric around the origin, and then, so that you didn't have to deal with half integers, you scale up by a factor of 2. So capital N minus 2 down, or capital N plus 1, and so on. If you do it this way, you don't have to distinguish between the parity of n. You get the same thing for each value of n. Now, the recurrence relation that the general Krawtchouk polynomials satisfy is minus x k sub n of x pn is an kn plus 1 plus bn kn plus cn kn minus 1. Now, if we let x equal 0 in these polynomials, we have a 0 sub k here. And if k is 1, 2, 3, or so on, you get a 0 as a factor. So the only thing that's left is the sum when little k is 0. When little k is 0, all these things are 1. So these polynomials are all 1 at 0. And so an plus bn plus cn is going to be 0, which you get when x is 0. So I only have to tell you what an and cn are. And you can see that if p equals a half, it's a half times 1, 2, 3 up to n, and capital N minus little n, capital N minus little n minus 1, and down to capital N. So, how do we, in fact, then show that that polynomial vanishes? Well, we take the recurrence relation, and we want to show that for n equals capital N, that this term is going to vanish. Now, it's going to vanish because this coefficient is 0. But we can renormalize and pull that coefficient over here. And so it actually vanishes because the case of capital N plus 1 is 0. Now, if we remove that term, we have to show that this identity is true for x equals 0, 1 up to capital N. And that doesn't look likely at all, because the left-hand side is a polynomial of degree capital N plus 1 in x, and the right-hand side is a polynomial of degree capital N. So these are not going to be identically equal as polynomials. They're just going to be equal on that set of points. So how do we do it? Well, the left-hand side, let me show you what that is. It's minus x k sub capital N of x p capital N. And those two terms drop out because they're neither 0 over this range. And so we're left with the sum minus x. The sum, k goes from 0 to capital N, minus x sub k over k factorial, 1 over p to the k. But now if I restrict x to be 0, 1 up to capital N, this term is going to vanish when you get to little x, which is at most as big as capital N. So we can stop the series there, and if we stop the series there, we can sum this by the binomial theorem, and we get that. Then you can do the same thing with the other side. It's a bit messier. You have two terms. You have to do the same sort of thing, put them together, and you see you end up with exactly the same thing. So for x equals 0, 1 up to capital N, the two sides are identically equal. So that remaining term then had to be 0. And it's 0 because the kn is 0, not because of the factor n minus little n. If it were 0 because of that, then it would be identically true all the time for all x. And that's not the case. So what else can one do? Well, I put up a chart for certain sets of orthogonal polynomials. Here it is again written upside down. Hermite polynomials are orthogonal with respect to the normal distribution. Krawtchouk symmetric, the binomial distribution. Meixner, the negative binomial distribution. These Meixner-Polychek are orthogonal with respect to the natural best continuous analog of the binomial distribution. There's a paper by Boas and Shisha in the Monthly on a continuous analog of the binomial distribution, and they don't use that, much to my sorrow. I was the referee of the paper, and at the time I didn't understand what was really happening, and their paper was correct and it looked reasonable. Later on I learned more, and the measure that they have has only finitely many moments. And this one has infinitely many moments. And this is really the right version of a binomial distribution. And you can see that when you write out what the polynomials are that are orthogonal with respect to each of these measures. They're the same polynomials with just different choices of the parameters and different values for the variable that you're using. But you can go above this in that other chart, or here below it. The Hahn polynomials were actually found by Chebyshev. When alpha and beta are 0, this is a discrete version of Legendre polynomials, and Chebyshev had them in 1855. 20 years later, he comes back to the question, and he's doing some data analysis, and he's trying to do extrapolation from data that he has on integers, and wants to find out a nice way to do that. And he'd done it with the uniform distribution first, and now he does it with respect to the binomial distribution. The polynomials that are orthogonal here extend the Jacobi polynomials, and if you let x become capital N times x and let capital N go to infinity, this measure goes over into the measure x to the alpha 1 minus x to the beta, which is the same thing as that. When you have a set of polynomials that's orthogonal with respect to a finite measure, like this, Pn of x, Pm of x, W of x, say x goes from 0 to n, and this is 1 over kn. Then you can write Pn of x, square root of W of x, as the square root of kn, as a matrix, and that's an orthogonal matrix by columns, and therefore it's orthogonal by rows. And so there is another orthogonality that these polynomials satisfy. Pn of x, Pn of y, Kn, doing something with them, and you're going to get 1 over W of x times delta Mn here, and now delta xy. In general, these things will not be polynomials, however, but occasionally they are. For the Charlier polynomials and the Meixner and the Krawtchouk polynomials, the Charlier polynomials are that, And they're clearly symmetric in n and x. And the Krawtchouk polynomials had this. And they're symmetric in n and x. The Hahn polynomials that, as I said, Chebyshev had, have this form. K goes from 0 to n, minus n sub k, n plus alpha plus beta plus 1 sub k, minus x sub k, alpha plus 1 sub k, minus n sub k, k factorial, qn of x, alpha, beta, n. And these are p sub x. Well, if I'm going to look at this as a function of n with the degree being x, interchanging n and x, this is a polynomial of degree 2x in n. But it turns out that it is a polynomial of degree x in the quadratic variable n times n plus alpha plus beta plus 1.
So this is which one's against the Hahn?
These are the Hahn. These are dual Hahn. Now, where do these things live? Symmetric Krawtchouk polynomials I found out about in the following strange way. Jaap Seidel, geometer turned administrator turned combinatorialist in Eindhoven, was visiting at Michigan State one year. And he called me and said that he wanted to talk about Jacobi polynomials and wondered if he could come over and talk about them. And I said, sure. They had come up in some of the combinatorial work that he and some colleagues were doing. And after we had chatted for 2 or 3 hours on Jacobi polynomials, one of the things that had been found was an analog of an addition formula. There was an addition formula for Legendre polynomials. It was found by Legendre and Laplace in the 1780s. And then for the symmetric Jacobi polynomials, Gegenbauer found an addition formula 93 years later. And then 93 years after that, Kornwinder found the addition formula for the general Jacobi polynomials. A student of Vilenkin in Russia, Rosa Shapiro, had done a special case of it, but I didn't know that at the time. The 93-year constant difference was sort of striking. And I said there's some interesting things starting to happen with another set of polynomials, Krawtchouk polynomials. Charles Dunkel had just found an addition formula. And he said, oh, I know all about Krawtchouk polynomials. I said, where? For Legendre polynomials, it's this. Pn of cosine theta cosine phi plus sine theta sine phi cosine psi is Pn cosine theta Pn cosine phi plus the sum, k goes from 1 to n. There's some coefficients, ckn. And then there are some other functions, r n minus k of cosine theta, r n minus k of cosine phi times cosine k psi, where these are the kth derivative of Legendre polynomials multiplied by sine theta to the k. This is an extension of cosine theta plus phi is cosine theta cosine phi minus sine theta sine phi. And then when you integrate it with respect to psi, you get the product of two of these is the integral of this. And corresponding things exist for all of these Jacobi polynomials if the parameters aren't too close to -1. And Dunkel had just found the corresponding addition formula here. It's a sum thing, and it's quite complicated. I can't begin to write it down. No. No. And it involves some other functions other than just Krawtchouk polynomials. It's a more complicated thing, but potentially very useful, as these things have been very, very useful through the decades. And so I asked Seidel, where did you learn about Krawtchouk polynomials? And he said, oh, they come up in coding theory. And I said, what the heck is coding theory? That's how ignorant I was at the time. But Krawtchouk polynomials come in the same way Legendre polynomials come as spherical functions on the sphere. And the sphere is a two-point homogeneous space. It's homogeneous in that you can rotate the sphere, take any point to any other. And if you take a pair of points on it, you can rotate those 2 points to any other pair of points that are the same distance apart. Compact, connected Riemannian manifolds that are two-point homogeneous are spheres, projective spaces over the reals, complexes of the quaternions, and a two-dimensional plane over the octonions. That's it. In all cases, the spherical functions are special cases of Jacobi polynomials. We don't have a complete classification yet for the discrete ones, but in the course of trying to do that classification, some new ones were found. Bonai spent a lot of time working on this. And one attempt at trying to do this classification was to try to find the polynomials that had the property that they were orthogonal and their duals were also orthogonal. A student of Rick Wilson's from Ohio State, who'd been heavily influenced by Bonai, talked on this at an AMS meeting, and he was convinced that the most general ones that existed were these Hahn and the dual Hahn polynomials. So I took him out in the hall afterwards and I said, no, that's not where you look. There are these polynomials, and I'll tell you a little bit more about them in just a minute, where else they arise. And then there are Q versions of all of these, and they all have the property that if you interchange n and x, you get polynomials in an appropriate variable. It's Douglas Leonard, and what he did is to prove that those are the only ones. In a very nice theorem. What? Why addition formulas are useful?
What way?
Well, let's just look at the corresponding integrated version. Now, we're interested in doing harmonic analysis on the sphere. And we restrict it to zonal functions. We're interested in series like this, summation an dnx. We want to do various summability methods, because in general this thing isn't going to converge if the function is just a continuous function. And so we're going to be interested in looking at an operator that applies to this function, something like the Cesaro means or the Abel means for the Fourier series. And when you put Tn in, well, if you're dealing with Fourier series, and you take Tn to be r to the absolute value of n, you get that this is going to be the integral of your original function f of theta times the Poisson kernel, 1 minus r squared over 1 minus 2r cosine theta minus phi plus r squared. Phi theta is going to be f of phi. But that's not what you really initially had, or cosine theta minus phi. You have to sum the series 1 plus twice the sum and goes from 1 to infinity. R to the n cosine n theta cosine n phi. And you can do that because you can reduce this down to just a single cosine. When you do the corresponding things with Legendre polynomials, you have the sum and goes from 1 to infinity. And you have to look at that sum. And that's an intractable sum to do simply. But if you can write the product of these two as an integral of 1, then you have just one of these things, and that sums to 1 minus r squared over 1 minus 2r x plus r squared to the 3/2. When you do the corresponding things with Cesaro means, the C2 means for Legendre series are positive. You can prove that at the end point by actually working with the series, but to do it over the whole interval, you need this integrated form of the addition formula. And there are many, many other reasons. It allows you to take problems in one variable as things that you can do and move them over to the two variable ones, which is what you need.
And the positivity is what you want, because this means
Right.
you use standard methods to prove convergence.
Yeah. And the positivity is crucial on all of this. So, now, the Hahn polynomials and the dual Hahn polynomials, the Krawtchouk polynomials were known as Lloyd polynomials for a while in coding theory because people didn't know about Krawtchouk's work. The dual Hahn polynomials were known as Eberlein polynomials for a while. And I wrote Pat Eberlein once and told her where these things came from first, and that almost all of these polynomials are misnamed. Laguerre polynomials were in Russia called Chebyshev-Laguerre polynomials because Chebyshev did them before Laguerre, but in fact Abel and Murphy had done them earlier than that. And Hermite polynomials were called Chebyshev-Hermite polynomials because Chebyshev did them before Hermite, but Laplace did them before that. And I said, you're in good company of having polynomials named for you, but somebody else had done them first. And she wrote back and she said, gee, this is great. I never thought it would be listed with those people. So these things arise in various combinatorial settings also. But they also arise in another place. In angular momentum theory in quantum mechanics, there are 3J symbols and 6J symbols. 3J symbols have two orthogonality relations, and they are the two orthogonality relations for the Hahn polynomials and the dual Hahn polynomials. The 6J symbols are, in essence, the Krawtchouk polynomials. Stu Lloyd got his PhD in Illinois in physics, and he worked in angular momentum theory. And he had done a lot of things with 3J and 6J symbols. And then he went to Bell Labs, and coding theory was getting started about that. It had been started a little before that. And he got involved. And, well, as I said, Krawtchouk polynomials were known as Lloyd polynomials. After all this stuff came out, and we began to understand how they all fit together, I saw Stu at a math meeting. And I said, Stu, did you ever realize how close your coding theory was to the work that you did as a physicist? And he said, no, he didn't. He didn't know that he was basically working with the same functions. Wigner was in Madison one time, and I was telling him all these things about the 3J symbols and 6J symbols being orthogonal polynomials. And he said, it can't be. Everything's a half integer. There's no polynomial variable. I said, wait till we get to a blackboard, and I'll show you. And so I put down a formula for the Hahn polynomials and the dual Hahn polynomials. And he said, yeah, you know, you're right. Now, Wigner was the first person to write down the 3J symbols. So these things can be buried. They can be very simple things that just don't come up directly And it wasn't in the polynomial form that these things came up from the algebra, that in the SU2 algebra that Wigner and other people were dealing with. So, now,
so how about interesting analogs of the South-Scalar program elsewhere? That involves the Krawtchouk polynomial.
The analogs of what?
Scalar.
Yes.
Do these have interesting analogs?
Yes. There's a paper of Delsarte that deals with Q versions of Krawtchouk polynomials. And it was that paper that finally convinced me that I needed to look at what was happening with Q series. Now, let me tell you just a little bit about another way of thinking about some of these polynomials, the classical ones, Hermite, Laguerre, and Jacobi. They all have the following property. Pn of x is an orthogonal polynomial, and the derivative with respect to x of Pn of x is the set of orthogonal polynomials. And you can write down what they are. The derivative of Hermite polynomials are Hermite polynomials. The derivative of Jacobi polynomials, you shift the parameter alpha and beta up by 1. So the fact that the classical polynomials have the property that the derivatives are orthogonal is a triviality. The non-trivial result is that if you have a set of polynomials that are orthogonal and the derivatives are orthogonal, then they have to be one of those three, Hermite, Laguerre, or Jacobi. And in the Bureau of Standards Handbook of Mathematical Functions, in the chapter on orthogonal polynomials, they start off with every set of orthogonal polynomials satisfies some conditions. The derivatives are orthogonal. They satisfy a second-order differential equation. They satisfy a three-term recurrence relation. I think there was a fourth one. Well, all polynomials that are orthogonal satisfy a three-term recurrence relation, but the only ones that satisfy the fact that the derivatives are orthogonal are the classical ones. The only ones that satisfy a very nice second-order differential equation are the classical ones. And the third one is a Rodriguez-type formula, which for our Jacobi polynomials says that the nth derivative with respect to x of 1 minus x to the alpha, 1 plus x to the beta. When you kick those up by n, you're going to get 1 minus x to the alpha, 1 plus x to the beta, Pn alpha beta x, and there's a factor that you have to put in to get the usual normalization. And formulas like this exist for all those classical polynomials. And some people think that's all there is. Well, all of the other ones here satisfy relations like this. In some cases, it's the finite difference. If the polynomials are orthogonal and their finite difference is orthogonal, then the polynomials are Charlier, Meixner, Krawtchouk, or Hahn polynomials. There's a divided difference operator that you can use that gets you the dual Hahn polynomials and the Rockoff polynomials. And you get these other ones if you do a finite difference or a divided difference operator off in the complex plane. So all of these have that, and there are Q versions of that. The analog of the derivative, you should look at f of qx minus f of x over qx minus x, and that's dq of f of x. And Hahn had a paper where he found all of the sets of orthogonal polynomials. They have the property that this operator applied to them gives you a set of orthogonal polynomials.
So fqx, these are the things that come when you replace x with these number theoretic sums over powers of q, or what?
You replace x to the n often by x times x plus 1 up to x plus n minus 1. When you're doing finite differences, you replace it by, well, you replace x by the x minus 1 over q minus 1. And then you just use an ordinary difference in x. The first person to do things like this was actually Fermat. When he integrated x to the n, he used a geometric dissection. Instead of an arithmetic dissection, you just have to sum a geometric series. Wallace also did that independently. But that isn't the whole story. There's another divided difference operator that gives you another set of polynomials that are special cases of the Q version of this. And I'd like to tell you just a little bit about those polynomials. They were found by L.J. Rogers.
Is this the same as the Rogers-Ramanujan identity?
In 1895.
The same person as the...
Same Rogers. In 1894, you got what are called the Rogers-Ramanujan identities. Found another identity of a similar nature that would be rediscovered by Atlee-Selberg in the 1930s. These papers of Rogers are remarkable for the depth of what he has and the insight that he had. Now, let me tell you where those things arise. If we take the Jacobi polynomials, alpha equals beta, and want to renormalize them to get a nicer generating function, we get a set of polynomials called ultraspherical polynomials that have this generating function. Their orthogonality is this. And their three-term recurrence relation is 2x times n plus lambda. Cn lambda x is n plus 1. Cn plus 1 lambda x plus n plus 2 lambda minus 1. Cn minus 1 lambda x. How do we get this up? Switch. You know, it would have been better probably for me just write on paper, but let's... I'm old-fashioned enough. I'm used to blackboards, and whiteboards are passable substitutes for blackboards. Stuff stinks. Now, what we'd like to do is to do a Q version of all this stuff. And Rogers had a Q version of this. We're going to take a number a and pull it into q to the a minus 1 over q minus 1. So we're just going to take this n plus lambda, n plus 1, and n plus 2 lambda minus 1, and write 1 minus q to that power over 1 minus q. And then we can multiply everything by 1 minus q, so we might as well forget that. And there are times when I'm going to want this quantity to be negative. So I'm going to replace q to the a by a. So we're going to look at 1 minus a q to the n times x. Cn x a q is 1 minus q to the n plus 1. Cn plus 1 x a q plus 1 minus q to the n minus 1 times a squared. Cn minus 1 x a q. And that's this. Rogers also had a generating function for these polynomials, and that's easy to get. You just write down Cn x a q r to the n, just as you would write down this. Take this recurrence relation here, multiply by r to the n, or n plus 1, and differentiate to get the n plus 1 and pieces of all of this stuff. And when you do that, you set up a you get a first-order linear homogeneous differential equation, which you can just solve by integrating. If you do the same thing here, multiply this by r to the n plus 1 and sum, call this generating function something, you get two terms with factors there, and then you iterate that. And what you get is this. You have the product, n goes from 0 to infinity. And we're going to want extra stuff down below. And up top, 1 minus 2ax r q to the n plus a squared r squared q to the 2n. If a was, say, q cubed, lambda then would be 3 in what we're looking at here, and we'd get 1 over 1 minus 2xr plus r squared cubed. Here we would get 1 minus 2xr plus r squared times 1 minus 2xrq plus r squared q squared times 1 minus 2xrq squared plus r squared q to the 4th. And then from then on, everything down below would cancel what's up top. And so this is easy to do. What isn't so easy to do is to come up with an analog of that. And the orthogonality is this: Cnx aq, Cmx aq. And then there's a product. K goes from 0 to infinity. You integrate with respect to dx over 1 minus x squared. That's the 1 minus x squared to minus a half. If we let x equals cosine theta, then dx over square root of 1 minus x squared is just d theta with a minus sign. And in here, you have 1 minus 2, and then you have 2x squared minus 1, q to the k plus q to the 2k. And down below, 1 minus 2, 2x squared minus 1, a q to the k plus a squared q to the 2k. And this is 0 for m not equal to n. And that's when a is between minus 1 and 1. We're assuming the same thing for q. The orthogonality exists for a slightly larger range of a than that. And in those cases, you have to add 2 discrete mass points as well as having this absolutely continuous part. Now, Rogers didn't have that. But he did have something else that was very important. We can take this series and take lambda equals 1, and 1 over 1 minus 2 x cosine 2xr plus r squared. If x is cosine theta, is 1 minus r e to the I theta, 1 minus r e to the minus I theta, and that's the sum sine n plus 1 theta over sine theta times r to the n. When x is cosine theta, these are what are called Chebyshev polynomials of the second kind. And then you can differentiate this series with respect to x. When you differentiate this one, you get the derivative of Cn lambda x with respect to x is 2 lambda Cn minus 1 lambda plus 1x. And then you can use that piece to start and get Cn lambda x is the sum of some coefficients Cn minus 2k mu of x. K goes from 0 to n over 2. And we can write out explicitly what those things are. Rogers found a Q version of this for these polynomials. He didn't have the operator. He had other operators that he used to do that. The analog of the derivative operator there is a divided difference operator that goes off in the complex plane that I'm not going to say anything about, but can be motivated. In his 1894 paper, Rogers had the Q version of this with lambda equals infinity and mu equals for different choices of lambda and mu equals 0, 1, and infinity. Actually, lambda equals minus infinity, too. And it was in his 1894 paper using those results. When you look at this measure, and you take 1 minus x squared to the lambda minus a half, replace x by x over square root of lambda, and let lambda go to infinity, this goes to e to the minus x squared. The same thing happens here. If a goes to 0, that's q going to, that's lambda going to infinity if a is q to the lambda. And you get a q version of Hermite polynomials. They have a number of very nice properties, some of which, in fact, many of which Rogers found. And it was solving this connection coefficient problem between these classes of Q ultraspherical polynomials, really Q Hermite polynomials. Minus infinity also turns out to be orthogonal, but they're orthogonal in the complex plane, and that took even longer to find the measure there. It's an indeterminate moment problem, so we have infinitely many measures. We don't have all of them, but we have a lot of them. And it was solving that connection problem that led Rogers to the Rogers-Ramanujan identities. You can do more than that. There is a Q version of the Wilson polynomials. Jim Wilson's polynomials are orthogonal with respect to this measure. Gamma of a plus ix, gamma of b plus ix, gamma of c plus ix, gamma of d plus ix, over gamma of 2ix in modulus squared. They're polynomials with degree n and x squared. And when you integrate with respect to this measure, you get 0 when m is not equal to n. There's a Q version of all of this and that contains these polynomials of Rogers. This 2x squared minus 1 is twice cosine squared theta minus 1, which is cosine 2 theta. And that's 1 minus e to the I theta, which is 1 minus e to the I theta, times 1 plus e to the I theta. Factoring is important, notwithstanding what the reformers in math education say about school mathematics. And trigonometric identities are important. Quantum groups exist. There are Q analogs of 6J symbols, 3J symbols. There are these corresponding orthogonal polynomials. There's an enormous amount of mathematics that's building up out of all of this. And I haven't said anything at all about the step beyond that, which didn't exist 10 years ago, and that's elliptic hypergeometric functions. There's an old theorem of Weierstrass that says that if you have an addition formula of the classical type, f of x plus y is some algebraic function of f of x and f of y, then you have just 3 types. And the third one is elliptic functions. Algebraic functions of exponential, and algebraic functions of elliptic functions. There are elliptic hypergeometric functions. They don't exist at all levels. They only exist at what's called the well-poised level, which is where the Krawtchouk polynomials really live. And it's a really exciting time, and I wish I were 40 years younger and could get involved in it. But I'm spending most of my time trying to see what I can do about school mathematics. So that's enough. Questions? It was so great to have some questions during the talk. Usually I intimidate everybody. Yeah.
Is this in any way related to what might have led Ramanujan to them, or was that something totally different?
Ramanujan was probably led to them through continued fractions. And Rogers was led to this by him not being able to solve a problem that had already been solved in what I think is a natural way. Hypergeometric series is a series summation an with an plus 1 over an, a rational function of n. A basic hypergeometric series summation an with an plus 1 over an, a rational function of q to the n. The analog of the hypergeometric function of Euler and Gauss, where you have two factors up top and two down below, with one of them being k factorial. That series has a lot of transformation formulas. And following Jacobi, we can show that easily just by writing down Euler's integral representation and making changes to variables in the integral. Heine had found some transformation formulas for a Q version of this. Heine was almost certainly motivated by some continued fractions that Eisenstein had done. And then I think a desire to try to synthesize Gauss's work on hypergeometric functions that Kummer had pushed farther, and then the newer work on elliptic functions. And he knew that what he was doing was related to both of them. And he had its transformation formulas. Student of Riemann, Tomai, found what I think is the right way to do the transformation formulas. The first one is really considered as a Q version of Euler's integral, and Tomai really understood all of that. And then when you have that, then you can get the rest of the stuff. Rogers didn't realize this. And what he tried to do was to get these transformation formulas as a permutation symmetry. And in the usual representation, it doesn't look like that at all. And he found another way of representing these things. And it was that that led him into these polynomials. So it was an inelegant solution that was much more complicated than it needed to be. But in the end, a very deep piece of work. And I'm wrong to call it inelegant, because it really is elegant. It's just not what one would think of once you understand what's happening. He was a wizard. Ramanujan was one of these magical wizards that Mark Kac once described the difference between a genius and one of these magical geniuses. A genius is somebody you can imagine doing what they did if you were only much smarter than you were. The magical geniuses, in his example, was Feynman, is you can't imagine yourself doing what they did no matter how smart you are. And Ramanujan is a perfect example of that. Rogers is the kind of person that's partway there. I can't imagine doing some of the things that Rogers did, but I can imagine doing some of the other ones. So.
What happened in the last 10 years? You're saying something about the last 10 years.
Oh, these elliptic hypergeometric functions have been developed. And we don't know what they're going to lead to, but hypergeometric functions basically start with Euler. And I think Euler probably in the 1740s, maybe even 1730s a little bit. And I don't think we really understood what was happening until the 1930s. So it took 200 years. Basic hypergeometric function starts a little bit with Euler, but then really starts seriously with Heine. And we didn't get to the corresponding place to even start to understand what's happening until some work of Watson in the late 1920s. So that took 100 years, and it was another 50 or more before we really had simple proofs of the basic fundamental results. So it took 150 years to get to the point where we really understood. Now, we know a lot more, so it's not going to take that long for the elliptic stuff. But 10 years is far too short a period to tell what this stuff is really going to lead to. And then there's all the stuff in several variables, really starting with McDonald's work. The really deep stuff. And that's fascinating. Hardy said about Ramanujan, it's a shame he didn't live 100 years earlier in the great age of formulas. My comment is it's a shame he didn't live 100 years later, when we're trying to do in several variables what took 200 years to do in one variable. And we need somebody with his insight into formulas to see what we can do in several variables. We got a computer algebra system that's a little bit of a help, but
Don't you have to already tell the answer first?
what?
Don't you have to tell the system already the answer?
Not always. So, other questions?